So welcome back. So last thing we've got to do on this section is talk about damped oscillations. And so here we got a visualization where we have a mass on a spring, and that's actually a lab we're going to do today, in fact. But let's say that the mass is not moving backwards and forwards through a pretty nice medium like air. Let's say the mass is moving backwards and forwards through a viscous medium, a more viscous medium, like oil or water. Then what we'd find is if we plotted a graph of oscillation position versus time, which is at the right-hand side, what we'd see is that the amplitude would decrease, indicating that there's energy been taken out of the system. And in fact, what the viscosity does is it acts like friction, and it changes the kinetic energy of the object into thermal energy. And you might remember from Physics 1 that once you go across that divide, it's very hard to get energy back from thermal energy into mechanical energy. That's what fuel and engines does. But by and large, mechanical systems on their own just take it a one-way street. It goes from the mechanical energy to the thermal energy. So it's important. I mean, you know, if we didn't have damping, then that pothole that I ran over 10 years ago would still be causing my car to oscillate backwards and forwards. It would never stop. So I like damping sometimes. Other times it can be a real pain, and I don't want it to be damped so quickly. So controlling it becomes quite valuable. The force for the damping is related to the velocity, which is a little bit unusual. If I go twice as fast, I have twice the force. And it points in the opposite direction. If my velocity is up, the force is a restoring force, so it points downwards. That's why that negative sign is there. Let me get my pen for that. That's why that negative sign is there. That's because it points in the opposite direction. This is a constant, which tells you basically the coupling between the object that's moving and the medium. More viscous, I would expect a bigger B value, less viscous, a smaller b. And the V is the velocity. The B is called the coefficient of resistance. Now, here's the bit that, you know, frankly, I'm never comfortable about, because it's kind of like I just show it and then I pull the answer out of the hat. But basically what we say is, well, if we say that the sum of our forces is equal to M times A, and of course my forces, I said X, but it just means, you know, position. We have a minus kx because of the restoring force of the spring, and I have a minus bvx because of the damping. And if I work on that, I get minus kx minus b dx by dt. That's going to be my velocity. Dx by dt is a velocity. And that equals ma, and a is d2x by dt squared. That's my acceleration. And I look at that and I go, oh man, that's a differential equation. And some of you will have done differential equations. Most people will not have done differential equations. And basically, we don't do differential equations in this. So the book, it's not just me, it's the book, pulls the answer out of the hat like a rabbit and says, oh, this equals a e to the minus b over 2m times t times the cosine of omega t. And you go, oh, yeah, of course, like that. Well, no, it's not of course. It's an answer that came out of the hat. So all I want you to know is that it's solvable. And then you can work out what the omega is for the situation, and you get, you know, what frequency will this be at? Will it be at the original frequency? And it will not. If you had no damping, that would be the original frequency, but because you got damping, it's modified. So the actual oscillation rate does change. And then, so what do I want you to know? I guess I want you to know this, and that is there's some terminology. We have under-damping, we have critical damping, and we have over-damping. Don't worry about that on that side even. And what does it look like? Under-damping is where you got a little bit of damping, but it's not enough to stop the mass from going through the equilibrium position, going into the negative direction and coming back again. So there's a little bit of a wiggle, and that's under-damping. Not quite enough damping to just bring you back to your steady state position. And then there's critical damping, and that is you put just enough damping that as quickly as possible you return to your equilibrium and you don't overshoot. And then we have over damping. You just made the stuff too viscous. And yeah, you don't overshoot anymore, but it takes you an age to get there. You got too much viscosity. For instance, you could put syrup in your shock absorbers, and it would be overdamped. You would basically just go back to your equilibrium position, but it might take a week for your shocks to go back to your equilibrium position. So I'd like you to be able to draw these graphs, name these graphs, and kind of just talk about them. You know, this is what goes on. Engineers love critical damping. If you're damping and you want to get to the equilibrium position as quickly as possible, go for critical damping. You know, cool. And then the next little bit is driven harmonic motion and resonance. We're going to do a lot about resonance later on, but what we're saying now is we have an oscillatory system, and it has a natural frequency. Depends on its mass, depends on K. It's got a natural frequency. You can hear it. The projector has a higher natural frequency than the table does. And you can summarize and say, well, look, it's a big table. It's a relatively small projector. It's made out of different material. There's a whole bunch of reasons why it should be a higher frequency or a lower frequency. But everything has so it gets complicated with real objects. So for instance, I suspect if I did a frequency analysis on this thing, there'd be a number of dominant frequencies. Because it's got one dimension across and one dimension lengthways, and there's other bits attached, so it would be a complicated sound spectrum for this. So, is there a natural frequency for this? There's probably a couple of preferred frequencies. So let's make the situation a bit simpler. Let's say I have a swing. That's only got one natural frequency. Let's say I have a tuning fork. That's only got one natural frequency. Even with something more complicated like a wine glass, that will have some natural frequencies, but I bet there's one that you can take as dominant. When you have a situation like that, if you imagine on the swing, imagine you go to this park with your child, and you don't pay attention to what they're doing. So rather than waiting for them to come back to you and pushing, and waiting for them to come back to you and pushing, and waiting for them to come back to you and pushing, imagine you just grab the chains and you just jerk them backwards and forwards at some wacky frequency. They're not going to get this big natural swing. It's going to be just jerked around all the time. You get the increase in amplitude when you match your driving frequency to the frequency of the swing. You know, when you push, when your kid's on the downward swing, you're adding energy. If you push and down the upward swing, you're cancelling stuff out. So when you have your driving frequency matched to the natural frequency of the object, very naturally energy gets put into the system rather than been taken out. So we get what we call resonance, which is this tendency to amplify the situation. The amplitude gets bigger and bigger, or in sound that manifests itself as being louder and louder sound. Or in mechanics, you may find more and more amplitude in your oscillation. And that can be a good thing. Maybe you want to make this horn that sends sound throughout the neighborhood. If you can drive your little horn at the same frequency that the horn naturally has, you'll make a lot of noise. It will just keep going. Whereas sometimes it's not desired. When I was a Boy Scout, I was told always to break step when you go across an old wooden bridge. You always break step. It's kind of funny. It's like, I'm not sure we used to march. We weren't like military Boy Scouts. We weren't kind of like, marching all over the countryside. But there is a tendency to match the cadence of the people you're walking with. Especially you put your foot where they put their foot, especially if you're going over rough terrain. So there's this tendency to kind of get in line. But what they said was always make sure you walk across individually and break step. And the story I was told was when the Romans came to Britain back in, 12 AD or something, they were marching over the bridge to show these Brits who was boss, and they marched in step across the bridge. And the bridge was a crude wooden bridge, and basically they hit the natural frequency of the bridge, and the bridge started bouncing more and more. And that's pretty good, actually. Hey, we'll really show these guys, until we got to the middle and the bridge broke and all the Romans were washed out to sea. I don't think that happened, but, you know. And if you've been to Busch Gardens, not that I'm advertising Busch Gardens, but if you've been to Busch Gardens and you go to, it used to be called Dragonland for the little kids. They have these like rope walkways. And there's always some middle school kid standing in the middle, jumping up and down at the natural frequency. And you're taking your like 4-year-old daughter, who's petrified, across the bridge, and you get a third of the way out, and then this kid starts bouncing up and down, and you've got to get past the young child, and you've got to kind of hold on to your daughter, who by this time is wailing because of this. And then your teaching instinct comes out, and you get this teacher's voice, and you say, I think you'd be better standing at the side. And the kid goes off, which was one of a good day in my life, but, you know. In fact, I was at a... So resonance, we're going to come back to. It's really important. There's some math here. I don't need to worry about that math. All I need to worry about is this idea that when you have the driving frequency at the same as the natural frequency, you will store more and more energy in the system, and it will be manifest somehow. Incidentally, when you tune your radio, when you're driving in your car and you press the button for that next radio station, you're tuning the natural frequency of your radio to the driving frequency of that station, and that's how you hear it. Your radio and your antenna pick up every station in the vicinity, but the natural frequency of your radio matches one of those stations, and so that's the one you hear. It's not that you don't receive the others, it's that you don't amplify them because you're not at that natural frequency. And that's a big part of what we do in AC circuits. So let me stop there.